Welcome to day 3 of Unit 3. This is quite possibly every calculus teacher's favorite section to teach. It's called related rates, and it's pretty much all word problems. But it's really the first time we get to see a practical use or application of calculus. So the whole idea is that I have some problem, things are changing, so I have some rates of change, and I'm relating those rates in order to solve for some interesting idea. So in this problem, I have a spherical balloon, and its volume is increased, air is being pumped into it so that its volume is increasing by 100 centimeters cubed per second. The centimeters cubed just represents volume per second, the change in volume per second. Okay. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? All right, so it's always important to draw a picture. I know that for this problem, it's actually not that important, but I'm really good at drawing spheres, so we'll draw one anyway. So I have a spherical balloon. We're pumping air into the balloon. At 100 centimeters cubed per second. Now, a good idea would be to note that this is a change in volume over a change in time. Okay. And what I'm asked to do is solve for the change in radius. So I'm asked, how fast is the radius of the balloon increasing? Okay. So that's where we're going to start. Now, there's a formula that relates the volume of a sphere to its radius, right? Volume is equal to 4/3 pi r cubed. Now notice that this rate is with respect to time, and the rate that I'm looking for, how fast is the radius increasing, is also with respect to time. So that's the variable with which we are taking the derivative. So the derivative of the volume, or the change in volume with respect to time, is equal to 4/3 pi r squared, drop the power down, times the change in r over the change in t. So what just happened here? Think of this as implicit differentiation. I have two variables here, and I'm finding the derivative with respect to a variable that's not present, right? The variable is t, is time. So when I take the derivative of velocity with respect, when I take the derivative of volume with respect to time, I get 1 times dv dt. And when I take the derivative of this with respect to t, this is just a constant, and this is a power rule. Drop the power down, decrease by 1, times the derivative of r, dr dt. So now some things will cancel, boom, boom, boom. I know what dv dt is. It was given to me. 100 equals 4 pi r squared dr dt. Now, this is what I want to solve for. I want to solve for the change in the radius with respect to time. So let's do that. Dr dt is equal to 100 divided by all of this. All right, so there's a variable here that we need to figure out, and that's what r is. Well, I want to know how fast the radius is increasing when the diameter is 50 centimeters, or in other words, when the radius is 25. All right. Now, this is an okay answer, but let's try to simplify this a little because our number sense is really good in BC Calculus. We're good with numbers. So let's see. This is like saying 100 divided by 4, right? And there's 4 quarters and a dollar. And then this is just telling me that I have, what, 20, I have 25 here and I have two 25s down here. So So 1 over pi times 25. That would be a simplified answer. Okay. And then what are my units? Because that's very important when it comes to related rates. Centimeters per second. Next up is the typical ladder problem. So we have a ladder resting, it's 10 feet long, rests against a vertical wall. The bottom of the ladder is sliding away from the wall, okay, at a rate of 1 foot per second. And the question is, how fast is the top of the ladder sliding down the wall? So let's start drawing my picture here. So I've got this vertical wall. We'll assume that it's outside. Right, maybe there's a window here, the windowsill, and it's a brick. I'm just kidding, I'm not going to draw that detail. We have this ladder. And it's sliding this way, away from the wall, at a rate of 1 foot per second. Okay. Now let's keep in mind, that is a change in distance, but how can I represent this in a meaningful way? It's definitely a change in time on the bottom. If we were to place an XY coordinate plane on top of this drawing, I could say that this motion is a change in X over the change in time. Okay. Sliding down from the bottom when it's 6 feet away. So at 6 feet, the ladder is 10, which means it must be 8 high. And the question is, what is dy dt? Dy dt is how fast the ladder is sliding down the wall. Alright, so let's get started. The only equation I know that relates those three quantities is the Pythagorean theorem. Right? Again, using implicit differentiation, I'm going to go ahead and integrate, or excuse me, take the derivative with respect to time. I get a 2x dx dt plus 2y dy dt equals a big old 0, because that's not changing, right? That length doesn't change as it slides back and forth. Plus, the derivative of a constant is 0. So, all right, now I have information for all of these values except the one in question. Right? X is 6. The change in x with respect to time is 1. That was given to me in the problem. Times 2 times the y distance is 8, and it's 8 when the ladder is 6 feet from the wall, times, let's see, what I'm looking for here, equals 0. So let's go ahead and solve for dy dt. I get 16 is equal to, 16 dy dt is equal to negative 12. Okay. And then dy dt must be equal to negative 12 over 16. So the answer here, dy dt, is negative 3/4 feet per second. And now let's talk about this answer before we move on. Does it make sense that this answer is negative? Well, with the way we set our coordinate system up, this direction is negative, right? Moving down the y-axis would be negative. Okay? If I had gone back and set my axis, my coordinate system up in a different way, and made this say, maybe this was negative 1 feet per second. It was moving away from the wall, so I decided that because it's moving away from the wall, I wanted that to be negative. Well, then this value would have come out to be positive. But that's because of the context that I set the problem up in. It would be said that the bottom of the ladder was moving away from the wall, and the top was moving towards the ground. So that would have been positive when that was negative. But we didn't set it up that way. We set it up with this blue coordinate grid, which made things a little easier to set up, and so we got a negative answer, which is fine, because it makes sense in the context. All right, so for example 3, we've got a water tank that's in the shape of an inverted cone. The base radius is 2 meters. The height is 4 meters. And we're interested in what's going on when water is being pumped into the tank at a rate of 2 cubic meters per minute. We want to know at what rate the water level is rising when the water is 3 meters deep. So let's start with the formula for volume. It's 1/3 pi r squared times the height. But the problem with this is if I go ahead and start taking the derivative with respect to time, I'm going to end up with a product rule here. And it's going to get real messy real quick. Plus, I'm not interested in what's going on with the radius. I'm only interested in what's going on with the height. So let's come up with a relation between the height and radius. Well, the height over the radius is 4/2. And if we solve for the radius, we'd have that the radius is equal to the height divided by 2. And that comes from the original information there. So making that substitution, I now only have h's and d's. All right, let's clean things up a little bit so it's easier to take the derivative of. H squared plus, or h squared times h is h cubed, and this is going to be over 4. Okay, or in other words, there's a 1/12 here, but that's fine. So let's go ahead and take the derivative with respect to t equals 1/12 pi times 3h squared, dh dt. All right, so let's see. I know what dv dt is. It's 2. And I know what the h is, the h in question is. It's 3. And this quantity is what I'm solving for. Alright, so let's go ahead and solve for dH dt and plug everything else in. Let's see, dH dt should then equal dV dt, which is 2. Okay. Times 4 divided by, I'm trying to do too much in my head and I'm going to make a mistake, so let me not do that. Okay. I will go ahead and simplify this and make that a 1/4. So we'll multiply by 4 and get 4 dV dt equals pi h squared. H is 3, so that's 9. Okay. And then let's come up here to finish things off. Nope, not enough space. We'll come over here to finish things off. So dH dt is equal to 4 times 2 divided by 9 pi. And that's going to be meters per minute. Alright, so for the final example today, we have your classic math classroom, 2 cars traveling in 2 different directions at different speeds. What's going to happen? So let's go ahead and draw a picture to model this scenario. So car A is traveling west at 50 miles per hour. Okay, so I have some car A traveling west at 50 miles per hour. And car B is traveling north. They're headed for the same place. And car B is traveling at 60 miles per hour. Okay. And the question's asking, at what rate are the cars approaching each other? Another word for that is, at what rate is the distance between the 2 cars changing when car A is 0.3 and car B is 0.4 miles from the intersection? So, this is what I'm looking for. The distance between the 2 cars at the instant that car A is 0.3 miles and car B is 0.4 miles. So at that instant, the distance between the 2 cars is 0.5 miles, but what we're interested in is the change in that distance. That's the thing I'm interested in finding. Okay. And why did I say the change in C? I used the change in C because I'm going to use good old Pythagoras' formula, a squared plus b squared equals c squared. And C just happens to represent that distance. Okay. So notice that unlike the latter problem, where I also used the Pythagorean theorem, C is changing. This distance changes as the cars get closer together. It's not a constant. So I am going to have to differentiate that variable. So we get 2a dA dt plus 2b dB dt plus 2 equals 2c dc dt. Okay, before we move on, let's identify what it is I'm looking for. That's it. I'm looking for the change in the distance between A and B with respect to time. All right, now, there are some things that we can cancel out, like the 2's, because there's a 2 in every term. So we'll just divide both sides by 2. And now we can go ahead and start plugging some values in. We know that the distance A is 0.3, but 0.3 can be represented as 3 over 10. Okay. The change in A, which is the speed at which the car A is traveling, is 50 miles per hour. That's a multiplication, by the way. Let's change it to parentheses. It'll be easier to see. All right, B is 0.4, or 4 over 10 times the speed of car B. And then we have 0.5, which is 1/2 what I'm looking for, dc dt. All right, well, let's go ahead and multiply both sides by 2, and I can cancel some 10's out here and get 6 times 50, 6 times 5, plus 4 times 6. Equals dc dt. Now we have to be careful here, because when we think about it, this distance c is getting smaller. So this needs to be a negative number. We should be expecting a negative number here. But at this point, I'm not going to get a negative number. I'm going to get 30 plus 24 which is a different number than I got before. Why? Oh. When I multiplied by 2, I forgot to multiply that by 2 and get 8. So I get 30 plus 48, which gives me what I was expecting, 78. The only problem is I was expecting that to be negative because the change in c with respect to time is decreasing. The physical distance between A and B is getting shorter as the cars move in towards each other. So we must have set something up wrong. So let's see what we've done. Well, notice that car A is moving towards a point. So that distance, A, is getting shorter. We should be representing that as a negative velocity. And car B is getting closer to a point. So this distance is also shrinking. So this should also have been a negative value, which would have made all these negative, would have made these negative, and makes my final answer negative. So the change in c with respect to time is negative 78 miles per hour. And we're done. I hope you enjoyed these 4 examples as much as I enjoyed solving them. Again, really fun problems, and when we get into class, we're going to do a lot of practice with these guys.